All good? Great.
Yep, looks great.
All right.
And so wait, before you get started, I would just like to introduce the University of Minnesota Twin Cities. Thank you for being here today.
Yeah. Well, good afternoon, everybody. Thank you for the warm welcome. We are very excited to be here. My name is Autumn, and I am here today with Megan and Kavin, representing the University of Minnesota. And we look forward to sharing our attached housing division project with you. So we'll be going over a project introduction, our design strategies, and our team and partners. So we are actually pursuing a retrofit project, and we have challenged ourselves with the ambitious task of regenerating a 100-year-old and abandoned brick building into net zero affordable housing. And our design strategy is based off of the principles of preservation, reclamation, and innovation, because we are preserving the architectural facade, we are reclaiming the abandoned structure as a community asset, and we're also innovating solutions that will ensure the building lasts for another 100 years. And ultimately, this project actually has a global significance because these types of inefficient, old, but really beautiful brick buildings are found all over the world, and we think they're worth saving, but they are a significant impact on energy consumption. So that leads us to our fourth guiding principle of replication. And we are pursuing strategies that are intended to be replicable for other buildings of this archetype in similar cold climates.
Our site is adjacent to downtown Minneapolis and is located in the heart of the Phillips neighborhood, which is one of the oldest neighborhoods in Minneapolis. This area is characterized by this building's archetype of historic masonry buildings. On a smaller scale, we show our site boundary and how the site is located in a transit hub with great walkability. Based on neighborhood demographics, we're following these 5 design strategies of affordable housing, home ownership, large multifamily units, intergenerational family units, and accessible units.
And our structure has actually been vacant and abandoned for over 2 decades. So we're working with a completely unsalvageable roof, brick deterioration on the utility brick that's on the sides and the back of the building. All the windows are either missing or outdated. We have an aging limestone foundation and a lot of really unique decorative elements like cornices and coining that need to be repaired. To the interior, there is no slab and no interior framing except for unstable floor beams that are embedded in beam pockets and uninsulated walls.
So is this worth preserving? We say yes. We think that the architectural character of the street facade with its historical context is worth restoring. We aim to preserve the decorative cornices, coining, and Chaska brick, which is unique to the region, without sacrificing performance. The Phillips Regen project will have at least 8 ownership units and a below-grade shared community space. You enter the building to the south, which is on the right side of your screen. Taking a right, we show a model of a spacious 3-bedroom multifamily unit, and to the left is a unique 2-bedroom unit with an attached studio designed for an intergenerational family that is accessible for grandma or could be owned by grandson.
Minneapolis is located in climate zone 6A, which is characterized by very cold winters and hot, humid summers. And we also experience some significant winter winds from the northwest. So all of our design strategies do have to accommodate a pretty wide range of weather conditions. The building is oriented to the south with the majority of the envelope surface area to the east and the west. And the west face is particularly exposed. And we anticipate that this will cause some significant solar heat gains during the summer, which will have occupant comfort and performance implications, and we're pursuing strategies to mitigate that. Our initial estimate also shows that this orientation could provide a rooftop PV capacity of somewhere between 60,000 and 100,000 kilowatt hours of renewable energy. And one of the biggest climate challenges I really want to emphasize is the impact of insulating masonry in cold climates. So this diagram shows the original uninsulated wall to the left here. The middle is the interior insulation approach. And the right is the exterior insulation approach. And as you can see in the middle, when we insulate from the interior, we drastically reduce the wall's temperature profile, which also reduces the wall's drying potential. And this puts the wall at risk for freeze-thaw damage and other masonry deterioration mechanisms that are caused by unwanted moisture. So the best approach from a technical standpoint is to insulate from the exterior. But because of our guiding design principle of preservation, we're actually taking a unique approach that combines the two thermal control strategies. So to the south, where there's that decorative facade, we are taking an interior approach that uses spray foam insulation. And then for the remaining walls that have the kind of ugly and deteriorated utility brick, we're taking an exterior approach that uses a drainable eave system that integrates to below grade exterior insulation that is spray foam applied using an excavationless technique that was developed here at the University of Minnesota.
Moving to HVAC systems, we created two distinct hybrid HVAC concepts. The first one being the air source heat pump with VRF heat recovery, and the second one is ground source heat pump with VRF heat recovery. And in our first concept, the idea is to have cold climate air source heat pump that will be connected to a branch controller for VRF heat recovery, which will then be connected to indoor air handlers that will be serving each unit. But due to limited space availability for our solar panels and to achieve net zero, we needed a system that is more energy efficient than this, which led us to our second concept. And in our second concept, the idea is to have ground source heat pump that will be connected to water source VRF condensing unit, domestic hot water tank, and a preheat tank. And downstream of the condensing unit will have similar VRF configuration as with our first concept. But this system will have better heat recovery and energy performance than our first concepts. So both of these systems can be easily integrated with good ventilation equipment like ERV or HRV domain to meet the ventilation requirement. And also, since we are using indoor air handlers, each of the units will get independent temperature control, and we can use good air filters to maintain the indoor air quality. So these are just some energy comparisons. We created our energy model with the existing building condition that showed an EUI of 78, which is in the energy intense and homes buildings category. So once we included our enclosure and HVAC updates, we were able to reduce it close to high performance buildings and home standards. So making these changes showed about 55 to 65% overall energy improvement than our existing building condition. So these are just some initial energy projections. Moving forward, we will fine tune our energy model and perform some cost analysis to finalize our HVAC concepts.
The team has identified that the most constraining codes are accessibility, fire, energy, and structural codes. We have been designing within these constraints and will meet or exceed these codes. Here's a timeline on how our team will get to the finals. Looking ahead, we'll focus on developing and integrating the three systems of enclosure, mechanicals, and renewables for the final submission. We still have optimization, environmental, and cost analysis to do. Our institution has competed in 5 previous competitions, and we have a large multidisciplinary team with 2 experienced faculty advisors.
And these are our partners, which include the existing owners of the property and our technical consultants, Copeland Building Envelope, or Envelope Consultants. And thanks again for the opportunity. We're ready for questions now.
Perfect. With that, we'll open it up to our 2 panelists.
All right. I guess I'll go first since I was quicker on the draw for the unmute button there. This was a good job, guys. I enjoyed this. It was a good job. I do have a couple questions. You did mention accessibility in some of the interior units. Is the entrance accessible? Or was the accessibility just really kind of like a walk-in shower as opposed to a tub or something like that?
Yeah, I will direct that question over to Megan, our architecture lead.
Yes, so when you enter the building on the south side, you'll have to ascend some stairs, but at the entrance to the north, the back entrance, there's a chairlift, like a clear hoistway, that makes the first floor and that basement community space accessible. So the units themselves are ADA accessible, and so is the entrance.
Okay.
And then
Go ahead.
Sorry, I was just going to elaborate a little bit. We anticipate you can't park on the south side, so all the parking will be to the north. So that's why our lift
Okay.
is in the back instead of in the front.
Okay. Okay. Yeah, I couldn't tell what that square was on the drawing. It just wasn't big enough on my screen. So I was kind of hoping you'd say that, but I had to check. I also noticed you said something about foundation repairs in there, but you just kind of mentioned them and didn't really say anything else about them. Are they extensive? Are you going to be able to actually fix the foundation and make this work?
So we're good structurally. It was deemed as structurally fit. So a lot of the issues are for moisture intrusion, since it is limestone, and over time it's the mortar that really starts to become particularly porous. So we are actually using this really cool excavationless technique that does not require full excavation around the perimeter to apply spray foam to the below grade portions. And so this will actually serve as a pretty comprehensive water and air barrier. And then, before we even get to that point, there will be really significant tuck pointing and other types of masonry repair that need to be implemented first.
Okay. I think you answered my last question, which was about the windows, because I am the window guy. So I do appreciate the fact that you're looking at shading or something on the west elevation. Is daylighting going to be a problem on the east elevation on that side of the building for those apartments?
They'll get pretty good natural light. Our estimate shows that daylighting it'll be more of an occupant experience thing than a cost reduction or an energy reduction.
Okay.
But the east and the west do have significant enough glazing ratios to begin with to offer a good lighting.
All right. That's it for me. I hope I didn't take up too much time, Alex.
No, that was great, Steve. The only question I had, were there any thoughts on the savings of CO2 emissions from rehabilitating this building?
Yeah, we are still working on the comprehensive life cycle analysis. But in general, like a rule of thumb we've come through with our research is a lot of times rehabilitating does yield reductions in embodied carbon compared to new construction. But since we're working with such an old structure, we do have to compensate for the envelopes and efficiencies by using a lot of different types of insulation. So we'll see if the retrofit rationale directly reduces or is comparable to new construction, but we're using a combination of different insulations because inevitably we do need to use XPS for our inverted roof assembly. And then we do need to use spray foam on the front facade because of its water properties. And so those are both carbon intensive, and to kind of balance it out, we're trying to use cellulose batt for the interior part of the roof insulation and the floor insulation.
Okay, that answers my question. Second, and you guys don't have this information, but in terms of were there any in doing that, were there any benefits to your targeted market that you guys from this design strategy to your targeted market?
Could you rephrase that a little more? Doing the
I guess throughout
insulation,
this,
or
well, any particular the performance aspect or the material selection, is there what is the best outcome to your targeted market?
so our main rationale for all of these selections is really comes down to durability. We want this building to last another 100 years for generations to come. And so since we're designing for intergenerational design, we hope that these units are for permanent home ownership. So the hope is that they can stay within families, and the building itself will keep being a viable option for housing for this neighborhood.
And I just want to say thank you, everyone. We are at time. So thank you so much to the University of Minnesota Twin Cities for their presentation today. We're going to move on to University of Missouri. at this point. So I invite the University of Missouri to join video, audio. We'd love to see your faces, and we welcome you to share your screen.
Do we have folks on the line from University of Missouri?
Let's give it 3 minutes, as their scheduled time is 12:25. Just checking, do we have anyone here from University of Missouri? This is what we get for starting early.
I'm not seeing any names from the member list on the website. Ah, there's somebody.
Well, let's continue to give them a few moments. And if anyone from University of Missouri joins, we welcome you
Hi,
to take the
this is us.
stage. Oh, welcome. We are so happy to have you here. So I would like to present University of Missouri. I welcome you to all share your screens. If you turn on your audio and feel free to share your presentation.
Okay, sorry, we got confused on the Eastern versus Central time thing, so we are getting that set up right now.
Okay.
Give us just 1 second, please.
Yes, absolutely.
And Claire, as you're setting up your screen, I'll just let you know that my background will change at the 2-minute warning. So you'll have 8 minutes for your presentation, and 6 minutes in, my background will change to give you a 2-minute warning. And then at the 8-minute mark, when we'll open it up to questions from Steve and Alex, my background will change to a time's up, and then we'll turn it over to Steve and Alex to ask some pointed questions that they have as our jurors on the panel. You're muted, Claire.
Are we available to share the screen now?
You should be. Yeah, you should be
Okay.
able to at the top of the screen, or there should be a share. Yeah, if you share screen and bring up your presentation when you're ready, that'd be great.
Okay, thank you so much.
And in case we failed to mention it earlier, we are recording these presentations to be able to review for our jurors throughout.
Absolutely, and
Thank
my
you.
apologies again for our miscommunication. Yeah, we messed that up.
That
All
screen
right.
share is loading now, and yeah, we can see the website and the PDF. And now
Okay,
it looks like the
perfect.
slides. That's great.
Okay, hello everyone. We appreciate you all taking the time to attend our presentation on the solar connection in the attached housing division. Our team is retrofitting 2 existing structures into 1 attached housing complex. My name is Claire Watkins, the team lead, and I am joined by Cam, Mark, Madeline, and Max. We are undergraduate architectural students with a diversity of engineering minors at the University of Missouri. Our faculty lead is Lyria Bartlett. We worked with several local partners to ensure the reality of the project. The site is located in downtown Columbia, Missouri, home to approximately 45,000 students across 3 college campuses, including the state's flagship university. Columbia, Missouri is located in a 4A climate zone with cool to cold winters and hot, humid summers. The site plan on the left emphasizes how close the project site is to university buildings, high-rent apartments, and historic apartment structures in need of a retrofit. This is a highly walkable region with close access to restaurants, religious establishments, and healthcare. Between 2020 and 2021, 40% of graduate students and 25% of undergraduate students reported experiencing some level of food insecurity. In addition, many students, especially international students, lack reliable sources of transportation and require housing within walking distance of their campus. A lack of affordable housing contributes to the high estimated direct cost of living per year. The image to the left shows a high-rent student apartment structure located adjacent to our site. The average monthly rent for this building and comparable apartments in the area is $2,000 per month before utilities. The structures that currently reside on our site are commonly known as the J slums for their close proximity to the University of Missouri's journalism school and their substandard living conditions. This is not an isolated instance. More often than not, students must choose between affordability and livability in order to reside close to campus. Our proposed design will provide an affordable and comfortable housing option for the many food and transportation insecure students. The existing condition of the buildings include non-ADA compliant entrances, an inefficient building addition, single pane windows, a standard double brick wall configuration, inefficient doors, and an outdated HVAC system. Utilizing the WELL building standards, our team has approached the design with sustainability and occupant comfort at the forefront. This diagram divides the project into 3 categories of social, environmental, and economic goals and how they overlap with each other. The constraints of the project include building code compliance, existing site conditions, and the preservation of the historic elements of the buildings. The proposed retrofit will address these constraints along with improving building efficiency and occupant experience. The existing space between buildings has transformed into an atrium that connects the 2 structures. It contains a staircase for access to the units and bike storage. The atrium will help to minimize the number of exterior facing walls and in turn improve building performance. The existing brick exterior will be maintained for historic preservation, but the interior face of the brick will be redeveloped into a structurally insulated panel configuration. Ramp systems have been added to create 4 ADA accessible units on level 1. Our team has added canopies raised 7 foot above the roof for HVAC clearance. They are sloped at a 31-degree angle to maximize UV absorption and direct rainwater into water retention tanks. Collected water will be used to maintain the communal garden. So these are the proposed retrofit floor plans. The basement contains a shared laundry room, a mechanical room, a storm shelter. The ADA accessible units are located on level 1 and are 1-bedroom, 1-bathroom apartments. Level 2 and 3 are accessed by the central staircase and contain 2-bedroom, 1-bathroom units. These are enlarged unit plans. The walls are color-coded to represent the wall types such as existing brick, tips load bearing, and interior and plumbing walls.
To provide occupants with more control over their environment, we have incorporated a variety of smart systems, such as mobile integrated HVAC and plugged load monitoring. Our proposed flower beds, communal garden, and cool flooring will enhance the occupant experience. A Mitsubishi ductless mini-split air source heat pump will be used to maximize heating and cooling efficiency, along with occupant comfort. A Mitsubishi ARV system will work with the mini-splits to provide fresh air and control humidity. During mild weather conditions, the buildings will utilize a radiant flooring system, while in extreme low temperatures, the 2 systems will work simultaneously. Polar double pane windows with vinyl foam-filled frames will ensure air tightness, and an electric heat pump water heater, which is 2 to 3 times more efficient than a conventional heater, will be used to provide water to the residents. These active strategies work in tandem with passive strategies to optimize human comfort and energy savings. Our team collaborated with a local firm, J Squared Engineering, to help integrate these systems into our design. The ductless mini splits will be located on the roof, and the water heaters will be located in the basement to maximize space in the residential units. Air will rise through the thermal chimney and cross through the units to help cycle fresh air into the building. For our PV system, we have decided to use SunPower Maxion 6 AC solar panels on the roof canopy to produce energy for the building. We chose this product because it has a considerably high wattage output for a multifamily residential setting. A portion of the basement has been converted into a storm shelter for increased durability. Our team chose to add a SIPS wall for its R40 value to the existing double weave brick facade. A SunVault storage system by SunPower will be used to store excess solar energy. This can provide several days of off-grid use when solar panels are unable to absorb sunlight during storms or snow. The existing condition had a baseline EUI of 53.87, which is much higher than the 2030 target EUI. The diagram to the right depicts the annual sun exposure onto the buildings, which guided our placement of solar panels for maximum efficiency. Currently, the space between the 2 structures receive very little sunlight. The varied sun exposure across each facade informed our decision to implement SIPs in our wall configuration. Because of how little sun the courtyard receives, we have proposed a central atrium that will reflect light down into the northern part of the building. Additionally, the new east-facing balconies allow residents to enjoy morning sunlight. Here you can really begin to see how effective the redesign can be. Our design has significantly lower EUI of 29.85 without PV, is 7.88 with PV. The HERS score without PV is currently 49. Our utility consumption and carbon emission also has seen a 73 and 69% reduction respectively. Our next steps with the project are to continue research, estimate costs, improve EUI and HER score, and develop construction documents. To conclude our design, we will mitigate the need for affordable student housing within close proximity to college campuses. Our project will also act as a prototype for a retrofit of similar structures in the area. Thank you for taking the time to listen to our presentation.
Awesome. Thanks, y'all. You've got some extra time for questions. So we've got 5.5 minutes and we'll turn it over to Steve and Alex.
Yeah, it's Alex. Great presentation. Were there any thoughts? And appreciate the team identifying a complex real world issue, right? Food insecurity. But in terms of this design, the strategy, or I don't know which entity the project team is working with, but how does the communal gardens, how are we ensuring that the communal gardens can address those food insecurities?
Yeah, so we are partnering with the University of Missouri's Tiger Pantry, which is a resource for students with food insecurity. Our goal is to kind of work with them. A lot of what they provide are canned goods and kind of boxed food that is easily transported and stuff, but we would like to provide fresh produce to them and work with the residents to maintain the garden and allow them to access those resources as well.
Okay, thank you. That was all that I had. Steve?
All right, thanks. I have a couple questions about the floor plans. Is there any way you could provide bathroom access that's not through a bedroom?
So we thought about that. It's definitely a possibility. Just the way that the kitchens are laid out, we would have to kind of rearrange that. With the 1-bedroom apartments, that could certainly be an option. The 2 bedrooms, it's more likely that the bathroom will have to be shared between the two, accessing through the bedrooms.
All right. And I think you answered one of my other questions too, and that is the roof. You're planning on capturing all the rainwater from the roof?
Yeah, that is mainly where we're gonna capture it from. Yes.
Okay. I was just a little worried about the one roof angling towards the atrium because
Yeah, so we have thought about that, and it's in design right now. It's not official, but we're thinking of having something on the edge of those solar panels where it captures it before it, goes down into that atrium. Just because, like you say, it's a bit of a problem, but we're working on that.
Yeah, you would not believe how hard it is to keep water out of the joints around that atrium. And then to divert more water on top of it would not be a good idea.
Yeah, we're also working on a different roof system for that as well, but that's what we got so far.
Okay. Yeah. Okay. I don't know. I think that was basically my questions about it.
I did have one more.
Go ahead.
Yeah. So on that storm shelter, what's the capacity? Is that going to house all the residents or?
Yes. So we worked in with giving each person around 10 square foot. I know it's quite a lot, but since we got 88 people, we would like for them to have, some space in there. But it's around 240 square foot is what we're thinking about right now. It will house everyone in that space, but we're still working on the exact number if we want to make it bigger or smaller, depending on, since it is an apartment, there might be more people there, during the storm. So we're still trying to take into that consideration, but yeah, we're thinking about everyone in that space.
Okay, and to piggyback off of that, were there any thoughts as far as duration, how long folks could shelter in that shelter?
So for right now, I think we're thinking it's 2 to 3 days in that space. But again, that's another number we're working on.
Yeah, it will depend on the battery cells that we also are placing in the basement. If however many we choose to use, will contribute to how long we're able to keep people down there.
Okay, thank you.
Okay, well, we're at time. Big thank you to University of Missouri.
Thank you
And
so much again.
Sorry for the delay.
yes,
Thank you.
you're fine. So next up, we have the University of Toronto. So we welcome you to turn your cameras on and turn on your audio and share your screen.
Hi, am I audible?
You are audible.
Okay, perfect. Just going to share my screen. Yep, we're ready whenever we can start.
Awesome. You go ahead and start and I'll keep the time and you can keep track of my background for those updates. Go ahead, guys. Thanks.
Hi, everyone, and welcome to our presentation on 15 Howland Avenue, an attached house making a difference in the housing affordability crisis. We are a team of 4 engineering students from the University of Toronto and Canadian Electrical Contractors Association. For the past few months, we have been working alongside Young Women's Christian Association, Parkdale Neighborhood Land Trust, and our faculty advisor, Ian St. Clair. 15 Howland Avenue is a 3-story attached house with a basement built in the 1980s and is located in the Annex, a historical neighborhood near downtown Toronto, Canada. The house consists of 3 separate dwelling units across 3 different floors above grade. Each separate family's unit consists of 3 bedrooms and 1 washroom. The basement unit is a common area shared by tenants for laundry and storage purposes. While Toronto is a growing city for real estate development, it has been faced with severe housing crisis in the last 2 decades, as nearly 50% of Toronto renters cannot afford the current housing prices. We partnered with Parkdale Neighborhood Land Trust, a nonprofit organization working to provide high-quality affordable housing, supportive housing, and community economic development programs for low-income families. The housing affordability crisis was further proven by a shelter cost income ratio or STIR analysis of 14 comparable houses in the area based on the median annual household income. We found that 13 of 14 of these houses in our dataset surpassed the recommended 30% STIR affordability by 2.5 times. By investing time and funds into retrofitting houses to be more energy efficient, tenants will save on utilities, resulting in even more affordable living expenses.
Yep, so going off of that, our design goals were to make the house net zero, make it really cost efficient, as well as maximize occupant comfort. So to do that, we combined passive building strategies along with upgrades to the active mechanical systems to ensure that our house is as energy efficient as possible. And for this, we first did an analysis of where the heat loss is occurring in the thermal envelope. And we found out that in order of highest to lowest heat loss, it was the exterior walls, then the roofs, then the fenestration, and lastly, the floors. So we went with high performance insulation materials for the roofs as well as the exterior walls. In terms of our fenestration, we went with high performance, low energy triple pane windows with bird friendly glazing. Okay, sorry, can you guys hear me? No? Oh, okay.
Yep, you're good. Keep going.
So we went with bird friendly glazing, and bird friendly glazing was installed because in Toronto, it's a big problem where birds hit the windows and they go into it. So we incorporated the local guidelines on bird friendly glazing to ensure that we can alleviate that issue. In terms of the facade wall assemblies, we went with sustainable materials, which are very low in embodied carbon, as well as GHG emissions, not just in the operational phase, but throughout the analysis, which was conducted cradle to grave. So this is just a few examples of our facade wall assemblies.
In its current state, the house relies on electric baseboard heaters for heating, with an exhaust-driven ventilation strategy. No cooling is currently provided in its summer months. we suggest installing air source heat pumps for efficient conditioning. Each floor will have its own outdoor unit shown on the left here, which would serve 4 separate ductless indoor units in the bedrooms as well as the common area. Each indoor unit is to be individually controlled by new smart thermostats, allowing tenants to customize space temperature independently of other rooms on the same level. Not only will the addition of cooling improve occupant comfort in the summer months, these heat pumps have a much higher efficiency compared with the original baseboard heaters since they have a much higher coefficient of performance. The improved building envelope with additional insulation also reduces demand for heating and cooling, and hence the sizes of the units. Moving on to ventilation and exhaust, we will have dedicated energy recovery ventilators installed in each room, cycling between supply and exhaust every 70 seconds. With a recovery core of over 90% efficiency, energy loss via ventilation is greatly reduced. The included MERV 14 filters would also allow excellent indoor air quality.
To decarbonize the house further, 4 electric tankless hot water heaters will replace the current 4 natural gas water heaters serving the home. This will save tenants a total of $367 per year. Each dwelling unit and laundry room will be served by its own instantaneous water heater for metering purposes. The tankless option was chosen as it avoids unnecessary heat losses that the storage water heaters have, and the maximum water flow rate of the units at any time does not exceed the maximum amount of hot water the heater can provide. In accordance with current Ontario Building Code, a backflow preventer will be added to prevent contamination in drinking water in the incoming domestic cold water from city services. As well, all current plumbing fixtures will be updated to low flow fixtures, and bathroom fixtures are selected to have WaterSense certification.
As for renewable energy, we have decided to go with solar power. The house has a large roof area onto which 44 solar panels can be directly mounted. Together, they can produce over 15,000 kilowatt hours of electricity annually, generating savings of over 2,000 Canadian dollars each year, as well as reducing the house's reliance on non-renewable energy from the city grid. Should it be needed, additional ground-mounted panels can also be installed to further increase production. Before the introduction of renewables, our retrofit improvements result in a HERS score of 47. With renewables, the score is further lowered to -1, making a net positive house. Next, please. With all the improvements mentioned in building enclosure, fenestration, the additional new mechanical equipment, and solar energy, there are significant savings in both energy and costs. Here's a breakdown of the anticipated energy savings each year. And as mentioned, we are producing more power than we are consuming annually. Next, please. Here's another breakdown of the cost savings. With potential net metering agreements with the utility provider, the house can even get credited on the electricity bill.
So in terms of the capital cost breakdown, our total retrofit comes to about $322,000 Canadian, which includes the facade changes, the fenestration changes, the mechanical, electrical, and plumbing fixtures that we added, as well as the solar panels. But we also went a step beyond and took into account miscellaneous factors, such as damages that can occur when installing, as well as demolition costs, because we're working on a brownfield development as we're retrofitting. So we took all of this into account, and this is our total cost. In terms of reaching our goal, we wanted to make it as cost efficient as possible for the tenants. So to do this, we will get reductions as well as very low interest rate loans from grants and financial incentives provided by both public and private organizations. So the City of Toronto, in our case, provides a lot of public initiatives like the Home Energy Loan Program, and private organizations like Enbridge provide rebates for retrofits. And if we go with the low interest loan that's provided for retrofits, it's about 0.5%, which is incredible compared to the market rate currently of 6.5% that's going on here. So we see this as a very viable solution that can be implemented financially. And also, since there are 3 separate units, the cost will be shared by 3 units. So it'll be much cheaper and the burden won't be on one homeowner.
Thanks, guys. So we're going to turn it over to questions from Alex and Steve.
Yeah, for sure.
All right, I'll go first this time, I guess. We seem to be alternating, but that's okay. I appreciate everything you guys did on the facade and with the engineering and everything. Did you guys take any or do anything with the inside of the building? You know, a lot of old buildings have a lot of small rooms. Could we open them up, maybe not have as many of the mini splits or something like that to lower costs and maybe even lower operating costs as well?
So in terms of the architectural changes, if that's the case, not to the inside of the houses, we saw that the tenants were pretty happy with the layout of the house and they had no concerns with the existing floor plan. But one thing we are in the process of adding is a fire plan. They don't have a fire safety plan currently in place. So we're adding a fire escape from the balcony of the second and third floor homes, so that they get easy access during fires. And as well, we're adding accessible ramps as well, because the ground floor tenants are actually elderly people. So we wanted to make the access easier for them. So those are the architectural changes we're working on.
Okay. I think that's it for me, Alex, if you have any questions.
Yeah, appreciate it, Steve. Great presentation. You answered my question in terms of um, life safety, right, from the third floor down to the ground floor. Another thing, in terms of the solar panels, any thoughts on for operations and maintenance of those panels being that elevated?
Right. So is the question on like how is that going to be maintained, or is it regarding the cost of the maintenance?
No, how like, you know, if it needs to be serviced or things of that nature being
So based on our orientation, and Martin can add on to this, but based on our orientation and tilt angle that we chose for each of the panels in the installation, we have it such that the snow, like we encounter a lot of snow, the snow just just goes off because of the slope with the panels. So there's not much cleaning to be done in that aspect. And we expect about a biennial maintenance, which will just be a cleaning of the roofs. And they already do it for the roofs in terms of the maintenance. So this will just be kind of cleaning the underside of the panels as well as just dusting them. But other than that, we should be good to go. There's no major concern.
Okay, and one last question with that. Is there a electrical disconnect for those panels? Any thoughts on that?
Electrical disconnect as in
Right, in the terms of if there was a fire up there, right? Is there a method, any thoughts on how to shut that off or isolate that? Because it's in a residential setting.
That's a great question. So in terms of the power supply or the DC power that we get from the solar panels, it doesn't actually go integrate back into the house. It rather goes externally into the grid, because if we make more energy than the house even requires, then our plan is to give it back to the grid, and that's how we get our energy savings. So we can control that, and we're going to have conduits going through to protect it from weather elements such as that.
Thank you.
Yeah, no problem.
We've got a minute left. Any questions from either of y'all, or I could jump in with one. You have heat pumps for space conditioning. Do you the climate there in Toronto? Do you have backup heat, or are those going to be a combined heat system to meet those coldest of days?
So the heat pumps that we have, they are rated for, I believe, minus 15 degrees. And I think on a design day, if you do 1% winter design day, Toronto is probably around minus 20 degrees. So I believe the primary heating is going to be with the efficient heat pumps. The secondary, we will just utilize the original baseboard heaters. That may bring up a question of inefficiency, but minus 20 design days don't occur all that frequently. So that should not be a big penalty on efficiency.
And also just to add on from the building envelope perspective, we set our design operative temperature for the occupants at 18 degrees Celsius. So all of the heat loss calculations as well as the design of the walls was based on that. And the walls are also certified passive house level and inspired from projects conducted here in Ontario. So they're particular to the weather conditions that we face in this area, which will help with that as well.
Thanks, Shell. Great. And with that, we'll wrap with that presentation. Appreciate it from the team. And
So yeah, so thank you, University of Toronto. We appreciate your presentation today. And with that, we're going to break for 10 minutes. I ask that everyone try to come back around 2:05 p.m. Eastern time. So 10 minutes, we'll meet you back here.
Thank you. Thank you to all the judging panel. Pleasure was ours.
Thank you too.
Thank you.
hey, Steve, and other folks, if you're on the line, I think we misspoke a few minutes ago. We actually have an hour now of break. So we have until 2:05 Eastern.
Okay. That's what I thought, but I was going by what Julia said.
I just crammed down some food thinking we only had 5 minutes or 10 minutes. But so yeah, so for those that are on the line now, if you're paying attention or if you're in the meeting,
Right.
we have until 2:05 Eastern or 12:05 Mountain Time, where Julia and I sit.
All right. I'll be back then. So
We
thanks.
apologize
Thanks
for
for
any
that.
confusion.
Nope, not a problem. I was sitting here working away, sending emails. It's all good. So Jeff, go get some dessert and enjoy it instead of cramming it down.
Have a good one. See you at 2:05 Eastern.
Yep. Gotcha. Thanks.
Thank you.
So Julia,
Alex,
yeah,
did
are
you
we
hear that?
breaking? No.
Yeah, so I was reading what I thought was the correct thing, and it was for a 10-minute break, but actually we have an hour and 10 minutes. So this is like your lunch break. So we're reconvening at 2:05 Eastern time, which I believe is 1:05 Central time, which I
Okay.
believe. So we will see you then.
All right.
And thank you so much.
All right. Thank you. Enjoy your break.
You too. Hello, everyone.
Whoa.
Hey, Julia.
How are you?
It's Friday.
It is. Okay, give us a minute. I think I see the Wentworth team. Yep. All right. So Jenna, would you guys, perfect. Would you like to pull up your presentation so we can just make sure everything is running smoothly?
Yeah, I can do that. Share. And then we did test it and it was good. So
Perfect. Wonderful. Well, let's give it a minute since others are joining.
And Jenna and team, just as a heads up that my background, I'll update with when you have 2 minutes remaining, and then I'll update again when the 8 minutes is expired.
thank you.
All right. Do you want to take things from here, Jenna?
Yeah, we can. Are we ready?
I think so.
Okay. Okay. Hello, we are the Boston Bay Builders from Wentworth Institute of Technology. Our team members are Indoni, Jacob, Non, Madison, and myself, Jenna.
Our attached housing project is located on 1778 Columbia Road in South Boston, Massachusetts, on the shore. Our project will be using shipping containers as a local resource from the only shipping container terminal in New England, which is located only a mile away from our site. The housing typologies surrounding our site are triple deckers, which is the local name for a 3-story apartment building. This story of housing was originally designed as affordable housing in Massachusetts for new immigrants coming to America. Currently in Boston, there is a shortage of affordable housing due to the pandemic. The average 1-bedroom apartment costs $3,000 a month, which someone needs to make at least $100,000 a year to afford.
Another constraint our site has is the flooding from nearby waterfront. As you can see, our site is in the path of the 2050 and 2070 1% storm surge risk. And then building on a wetland, we've created solutions to the topic of sea level rise. Here you have the site dimensions and the max height we can build per Massachusetts Building Code, and our FAR is 1.77.
Our goal for this project is to design affordable housing by using local and reusable resources, water and energy collection, and sustainable materials.
This 1-bedroom apartment is split into 2 units per floor. The floor plan allows future expandable space in the back. The space can be used to add an additional bedroom or any multifunctional space that fits the user's needs. We utilize the wall cutouts from the shipping container and ran a trace wall for plumbing through the center. This is our 2-bedroom unit showing the expandable space being used in the back. This is one of many ways to use additional multi-use space. This is our 4-bedroom unit with 2 baths, showing the 2 separate units being infused into a large 2,000 square foot apartment. This is done by simply demoing 2 3-foot walls to create a simple and effective central circulation. The floor plan can be customizable once the owner buys the neighboring suite.
We are using an 8.5 feet wide and a 9.5 feet high shipping container.
And the cost per unit in this area ranges from $980,000 to $1.15 million. Our new attached housing unit is only $385,329 added with land and construction costs. The estimated cost of construction for our building is $311,978. This was possible due to our material selection. Since 45% of our building is made from using reused and recyclable shipping containers, it is reduced our framing costs, exterior finishings, and structural costs.
We are using an 8.5 feet wide and a 9.5 feet high shipping container. The shipping containers contains 4 posts that are attached by a bottom and top rail, which are wrapped around with corrugated panels to provide structural integrity for the containers. We will remove our cutout pieces of the shipping containers, and we know that we have to reinforce it with a channel system for the containers to maintain its structural integrity. By separating 2 containers 22 feet apart from each other, it allows us to create space in the middle where we would have a post and beam structures to help evenly distribute the load from the upper floors. The shipping containers are stacked vertically connected by manual twist locks. For our foundation system, we are using a 6-foot deep plinth to hold up the containers. The plinth is raised 2 feet high from the ground, where the shipping containers are welded to a steel plate that is bolted through the grout bed into the foundation. We did a 4-to-4 connection drawing to show how we will be connecting and insulating the containers, as well as showing how we are using blue laminate beams to help move the load from the open space into the containers, which then helps transfer the load to the post. By using therm, it helps us to determine the amount of heat that is leaking within our 4-to-4 connection and showing us that the R-value of that connection to be 26. Here is a roof drawing showing how we will be adding in a parapet as well as a green roof to the containers to help gather rainwater.
Here is a cross section showing our design around flooding. We raised the building on a 2-foot plinth to accommodate for future sea level rise. The red arrows for our chase walls are also being borrowed from the shipping containers walls. And this is a long section showing our building cut through the green roof and triple stacked shipping containers.
Here you can see how we're using our roof as a solar pavilion to generate 236 kilowatt hours of electricity per year. And we actually have 12 of those solar hot water panels where you can generate hot water as well as electricity to offset all the electricity used in the building and help mitigate hot water needs. And we're actually collecting over 3,000 gallons of water every year, which is a quarter of our overall usage. And here you can see on the top those Midtrex clear solar panels and a mechanical penthouse in a container to make it waterproof, and our rainwater channel to the back. And on the back, you can see our expandable areas for bedrooms and general space, our rainwater tank. And if you move to the front, you can see how we have our greenhouse front on our stair core to generate hot air to keep the front warm, and our Matrix clear panels to generate even more electricity. And if you move into the unit, you can see how we're using the systems that are Energy Star and Water Sense to make sure that we're using as little as possible, and smart sensors to make sure we're not wasting, keeping our utilities low at only $86 a month per unit. And here we're using energy recovery ventilators to make sure we're not having to heat or cool any air. And we did a CFD simulation to show that our intake and exhaust cause the most airflow to be in key areas like the kitchen, bedroom, and bathrooms.
And then as you walk through the entry, living room, and kitchen, you will be immersed in recycled, locally sourced, and sustainable materials such as bamboo, linoleum, and recycled glass. And then continuing the sustainable materials throughout the home, ethically sourced elements include stone in the tile in the shower, cashmere bedding, and bamboo furniture and vanities.
Here you can see how our embodied carbon is very low. A study from North America showed that the average single-family home is 40 tons of CO2, while ours is only 15 tons per unit. And over our 100-year analysis, you can see that we generate 24 tons of completely net positive CO2 offsets. And with all these sustainable materials and systems, our PERS score is only 29 without any solar. With our large solar pavilion, it gets to -21, meaning our LEED score is 84 credits, so LEED Platinum, including regional priority credits such as on-site photovoltaics and runoff control.
And then from this stage, we plan to improve our affordability through materials and systems, discover new construction methods to maximize efficiency, further our building envelope typology, incorporate native plants, and continue to design against sea level rise, incorporate new interventions within the interior for maximum comfort, and lastly, adjust the overall sustainability of the units. Thank you. We'll now take questions.
Awesome. You ended the minute early, so we'll turn it over to Alex and Steve, and you have 6 minutes of questions then.
Good afternoon. Great job on the presentation. Real quick, were there any thoughts in terms of the project, how to go about selecting the potential shipping containers to be used for a project like this? In particular, the long-term effects like environmental concerns for the future occupants.
Yes, so we specifically chose our shipping containers from a locally resourced site near the area, which is to reduce carbon emissions because it's only a 3-minute drive from the site. So that is the whole reason we chose to use the shipping containers. And also another reason we chose to use shipping containers, going with a question about what sizes we used, we wanted to use a size that is suitable for the user. So we wanted to go with our larger shipping container with a 9.5 foot tall span as long as 40 feet wide. So we used 6 of those containers, and using those 6 would reduce our costs as well instead of staggering to different sizes inside the building. So it was more costly and effective that way.
Okay, thank you. And the only other question I have, by any chance, do we know well, there's 2 questions to this, the capacity of the solar hot water heating, which is a really good strategy. And also, were there any thoughts on the supplemental heat as a backup to the solar hot water heating?
Yeah, so we're using the solar hot water as kind of the way to make sure that we're using minimal heat for the hot water, but we're also using in that mechanical penthouse a heat pump system with mini splits. So each unit has heat pumps. So we're basically separating airflow and air circulation from heating. So we don't have to heat up air to keep the units warm in winter, which is a huge problem in Boston. So by using the solar hot water, it's not just for kind of keeping the units warm, it's also so that sinks, showers, etc. can get hot water very quickly. And also these solar panels, because they have hot water on the back, it makes the solar panel itself more efficient. So it actually gains more electricity when in operation.
All right, appreciate it. Thank you. Steve?
All right, thanks. Yeah, good job on the presentation. Going back to your flood estimates, it could be that I read them wrong, but it really looked to me like, especially the 2070 flood estimate, made it look like the building was going to be an island. And I kind of question that as being, okay, is this the best site to build on if that's going to be the case? So did you give any thought to that?
Right, so we want to go further into further development with that in our future project, going to the final. Just to think if what we did know by calculations is that we raise our building by 2 feet, and that's the surge for 2070 is around 1.5 feet. So we wanted to mitigate that by raising the building slightly.
Yeah, I understand that, and that was great. But I guess my point is, if are people going to be able to access the building if it's surrounded by water?
Yeah, so
in 40 years.
So as you can see, the site also abuts on a road towards the back. So we're using that as a circulation area. So say they raise the street a little bit, you can mitigate that. But also the reason we wanted to choose this site is our goal for the finals to be able to use the water that does flow under the building to possibly either get gray water to be used in the building or to use it as, for example, a geothermal system. So our goal is to not use it as a hazard, but to use it as an advantage of the fact that it will flood. So it's not just a resilient solution, it's hopefully using that flooding as an active system to make the building better.
Okay, right. Thanks. I think that's it for me.
All right.
That's it for me. Shout out to the guy wearing the shirt and tie.
Yeah.
Well, thank you so much to Wentworth Institute of Technology. Let's take a few minutes for the judges to take any notes, and then if the University of Arizona would like to start setting up their PowerPoint, you're free to do so.
Thanks so much.
Thank you.
Thank you.
Thank you.
Well done, y'all. Yeah.
Thank you.
Thank you.
Thanks.
Share screen.
We're just taking a quick second to get set up here.
Oh, take your time. The jurors still have a few minutes for taking notes.
Okay.
Perfect.
All right, so we would like to welcome the University of Arizona to get started. Thank you so much for being here today.
Yeah, thank you. The US spends over $1 trillion on energy each year. This cost is a big burden to people in South Tucson who spend an average of $130 a month on electricity because their only housing options are energy inefficient. For many, that's 10% of their income. Our team's goal is to create a net zero housing solution that puts $130 back into the pockets of residents each month. Our proposal is Casa Verde, a row house prototype with a series of rented studio and 1-bedroom apartments to infill sites throughout Tucson. We've used 3 big moves to keep net zero building affordable in the Arizona desert: a vernacular courtyard form, prefabricated shared walls and utilities, and the use of radiant services.
This site was selected for its access to transportation and city amenities. Row house units aligned east and west minimize summer solar gain in the cooling climate. They are grouped in sets of 6 to meet local zoning restrictions. Casa Verde takes the idea of courtyard living, which has been used in Tucson for hundreds of years for passive cooling, and implements it on the scale of the block to create a shared neighborhood courtyard. We are leaning into the local building character with thick stuccoed walls, small opening, light colors, and native vegetation.
Behind the stucco exterior is a prefabricated wood-framed wall. We partnered with Habitat for Humanity to use their brand new development center right here in Tucson, where volunteers use jigs to pre-build wall panels that are brought to the site. The project frame is designed with 8 panel types on an 8-foot module to fit on a truck and minimize waste. Once each panel is framed, plumbing and additional thickness is added. Sheeting is then added for one side for stability. From there, panels are loaded onto trucks and brought to the site. Walls are put up rapidly before being capped with a roof, filled with insulation, and covered with finishes. We're meeting again with Habitat to further refine this process, but we believe that we can drastically increase the ease of construction, reduce material waste, and increase scalability, all while increasing quality and decreasing cost.
Each unit has a sound insulated mechanical room that contains the equipment with an exterior door. We're using a radiant cooling system for its energy efficiency in this dry climate, but we reduced the cost by cutting the amount of heat pumps and buffer tanks from 12 to 2 that are now shared, with each unit controlled separately by its own manifold. In each unit, the ERB pulls in hot, dry exterior air and transfers some cool fan moisture. There is a separate dehumidifier in each unit that will only be needed during the 2 months of monsoon season to prevent condensation when the dew point is higher than the 60 degrees of our radiant cooling system. Plumbing systems are all embedded in the shared walls. This is initial design, and we plan to do a cost-benefit analysis to determine how quickly this high-efficiency system can pay for themselves to be worth the higher first cost.
Casa Verde's key strategy to increase human comfort has been to implement radiative surfaces, a regionally traditional way to provide more effective temperature control and better air quality than forced air systems. Historically, thermal mass is regulated diurnal temperature swings. We've elected to cool passively with phase change materials and actively with radiant cooling. One wall is freed by pushing all the utilities to one side and hanging phase change panels on the other, which contain materials whose melting point is close to room temperature, allowing them to regulate temperature. We've also designed a natural privacy gradient to increase social comfort.
To improve durability in the dry desert, we've designed the envelope to FIA's prescriptive standard. The wall are a wood Larson truss, and the roof is TGIs with a dropped 2x4 ceiling, both filled with cellulose. The slab is insulated, and the windows are double pane, not triple pane, because heat loss in the night during the cool season actually helps reduce overall use in our climate. In case of power outage, we've used passive design methods like cross ventilation, daylighting, and phase change materials that, according to climate consultant, make it comfortable 55% of the year without active systems.
Our goal is to minimize Casa Verde's carbon footprint to 25% of a comparable new building. The 3 biggest impacts we felt we could control were in structure, insulation, and roofing. Advanced wood framing, cellulose insulation, and recycled aluminum are economical solutions that have low carbon footprints compared to their counterparts. Making an educated decision on a material like recycled aluminum takes a lot of research. We've referenced different third-party environmental product declarations to arrive at a global warming potential of new aluminum roofing. Subtracting out the energy of raw material extraction, initial refinement, and adding back the energy to recycle aluminum, we've arrived at a 91% embodied energy reduction. In the coming weeks, we plan to use building emissions accounting for materials, or BEAM, and Tally to quantify our carbon footprint.
We have used 3 key strategies to make net zero buildings affordable in South Tucson. First, the vernacular courtyard form optimizes solar rotation, allows natural evaporative cooling for plants in the courtyard, and provides a balance between community and privacy. Second, the prefabricated shear walls reduce material usage, allow shared system for increased efficiency and lower cost, and create open floor plans for daylight, and to let phase change materials charge and discharge to effectively condition the space. Third, passive and active radiant surfaces take advantage of Tucson's 30-degree temperature swings for cooling benefits and improves energy efficiency, human comfort, and air quality relative to forced air systems.
Those integrated strategies are critical for improving the energy performance. Our emphasis on passive design, efficient system, and simple form with a continuous thermal envelope cuts the EY from 53 to 20 BTU per square foot per year. From there, solar panels on the slope roof meet the peak energy need. We've designed the building to FIA's prescriptive standards and plan to meet FIA's core, so we are confident that Casa Verde can be zero energy ready. We plan to take the project into UFI energy modeling software next to confirm this data. As discussed, we've made a few moves to meet those energy performance goals while remaining affordable. We've estimated a construction budget based on the similar projects in the area, and our next step is to break down our exact cost in RS means. We're working directly with the city of Tucson to explore funding sources that could make a Casa Verde a reality. South Tucson has a poverty rate of 51%, and of the 360 renters who move into the community each year, 160 make less than $15,000 a year. Many are single parents or young people in their first jobs. By significantly reducing their energy bills, Casa Verde has the potential to put money back into the pocket of those who need it the most.
We've been working with Tucson's housing development manager, and she's excited that our partnership with Habitat can make this project scalable to city-owned sites throughout Tucson. In this way, Casa Verde can help lower our collective energy consumption by making sustainability accessible for all. Thank you.
Perfect. And with that, we'll turn it over to our two panelists for questions.
Good job, guys. That's very nice. I really like the phase change walls that you put in there. That was a nice touch and a good design choice. I do have a question. Well, first of all, you answered one of my questions. I was really confused by the dehumidifiers with you guys being in the desert. So I appreciate the explanation on that in the presentation. So good job there too. I do have a question about your target market though, because if I looked at it right, it looked like every unit was 1 bedroom and it was about 500 square feet. So I'm just wondering if your target market of like single parent families is really going to be interested in that.
Yeah, that's a great question, and thank you for bringing that up. That's something that we missed in this presentation, but we have planned 2 unit types that fit within that same 500 square foot area, a studio and a 1 bedroom to allow increased privacy when we have, for example, the single parents and a child that are moving into the units.
Okay.
Yeah. The other piece here is that South Tucson is really a low income neighborhood. And so making these units as affordable as we can and bringing it to
making it affordable for people who can afford $500 a month. That's why it's 0 and 1 bedroom and not 2 bedroom. Which is,
Okay. Yeah. I mean, it's more a question as long as you've thought about it. You know, I'm not there. I don't know, so we have to ask. You know, just to make sure that you've covered it and it is going to work. So,
understood.
Alex.
Yeah, appreciate it, Steve. Looks like architects, right? Everybody's wearing the black uniform, so kudos. Can you go back to the prefab shared walls? What is that again?
Yes, Kedar, would you mind touching on this question? You looked into that a lot.
And the other question I had, sorry, I didn't mean to interrupt. Any thoughts on the courtyard, the landscaping? I didn't hear anything on that.
I'd love to talk about both those things. So we've designed this project with prefabrication in mind, so we can optimize the we can make this project as affordable as we can. We can reduce the waste of materials. The wall panels themselves can be made at a higher quality. And so we're doing that prefabrication on both the exterior and interior walls. The exterior walls we're adding a Larson truss to, a modified Larson truss to get a little bit of exterior, a little bit extra insulation in. The interior walls we're adding the plumbing into during that prefabrication step. So we can prefabricate every other wall to be plumbing and every other interior wall to be phase change materials. Your other question on the shared courtyard was central to our design. we're really excited about it because it provides a breath of fresh air to Casa Verde and the surrounding block. Being able to take the vernacular form of the courtyard, a form that's been around for hundreds of not thousands of years, and reappreciate the value that it brings really means a lot. And filling that space with less vegetation and offering benches and tables for the community allows the projects to have a bigger impact than just its lot lines. So.
All right, thank you. Great job.
All right, if there are no more questions, we'll just take a few minutes to allow the jurors to take down any notes they might like to take. Thank you so much to the University of Arizona. We appreciated your presenting to us today. And if Ball State would like to go ahead and start setting up their PowerPoint and preparing, we'll be starting at 2:35 Eastern time.
Thanks so much, team.
Thank you.
Thanks, folks. Good job.
Oh, all right. I'd like to welcome Ball State to turn on their cameras, and we look forward to your introduction.
Good afternoon. Today we will be presenting our project, Row on the River, which is located in Muncie, Indiana. This project was developed by Mokel Studio, which is developed a collaboration between 7 architecture students from Ball State University. Prior to going into this project, we understood that Muncie suffers from several issues, including poverty, lack of housing options, and a large amount of vacancy. Therefore, we wanted to create a module that could be applied to several infill sites that provides affordable housing to the residents that is also energy efficient. We first took a look at 3 neighborhoods to identify where these vacant lots were, and although many of these are non-compliant parcels due to the fact that they are too small and after setbacks, there's not enough buildable area. Muncie's comprehensive plan does recognize this and are updating the zoning codes to promote development in future years. And this zoning code is expected to be released in 2023. Despite future development, we are located within walking and biking distance of several recreational parks, the river, educational facilities, and an open door health clinic. These sites are also connected through the bus system and connects the residents through several areas throughout the city. We are also located outside of the historic Old West End, which is mostly single unit family residents, and the downtown, which has a lot of mid-rise apartment buildings. Therefore, we decided to choose a row housing typology that fills in this missing middle and creates a blend between these 2 housing typologies. The site that we decided upon is located at 300 West Washington Street on the corner of Franklin Street. And after considering the setbacks and the 2 alleys that are in this area, we were able to put 5 row housing units in this location.
Now, getting into the design process of our building, we started with a typical row housing typology and started to implement a series of architectural interests that really started to improve key elements of our design in terms of passive and solar strategies. We have 2 unit types, 3-bedroom, 2-bath, and 2-bedroom, 2-bath units that we initially put together using an adjacency matrix we put together early on, which helped us identify the relationship between many of the spaces in our building. As you look at the first floor plan, there are 5 units, and each unit has a relatively open floor plan, which was important to us because we wanted to take a lot of the southern exposure on site and really stretch it through the entirety of the space to naturally light up the building. As you can also see, centralized towards each unit, we have most of our mechanical and plumbing systems, which also continues up to the 2nd story, where you can see a lot of those utility rooms, such as our washer, dryer, and mechanical, also occupy that same central space. On the north and south, we also have our bedroom spaces, which really try to make use of a lot of the natural lighting on those exposed faces. To achieve the high insulation values we have so far, we took into consideration 2 primary building systems that we found would help lower the embodied carbon of our building. As you can see on the left, we wanted to work with a plywood slab, which was really important because we thought it would eliminate a large portion of the concrete usage, which in turn has high embodied carbon. If you look to the right, given our climate being in a lot colder area of the United States, we wanted to implement structural insulated panels for the exterior wall system. That way we could really try to eliminate the amount of thermal bridging that's penetrating into our building. Material-wise, a lot of the surrounding context has this sort of darker palette. So playing into the surrounding buildings, we wanted to stick to darker browns, blacks, and grays, whereas the interior stuck to a lighter palette, which was important when we try to bring in a lot of that natural light. We wanted to sort of diffuse it into the space and really try to reduce the amount of artificial lighting we have to implement. Continuing with materials, we wanted to put a heavy focus on material lifespan. At a slight cost increase, we wanted to have materials that were 2 to 3 times longer in lifespan, while still putting a heavy focus on keeping things affordable. Our estimated construction cost, we were aiming for around $250 per square foot. And we also estimated that around $41 would be implemented towards each exterior square foot.
Along with that, for our system, we're always looking at a heavy R value for our walls and ceilings. So our R values for the wall is about 36. For the roof, it's about 67. For the windows, we're looking towards double pane, low E argon filled systems. And we're also looking at additional active and passive systems such as stack ventilation and solar panels to help boost that efficiency of the building. For the passive systems, we want to look at stack ventilation in particular because that was one of the few passive systems that we found that actually worked well in our region. And through that, we just open up those windows and let the air flow out, bring hot air up through a clear story window. And we found that through testing, we would add an additional 989 indoor comfort hours without mechanical systems. And we also wanted to focus on rainwater catchment since Muncie is very well known for flooding. So we want to introduce some sort of water catchment systems, and going towards in the future, we want to focus on how we can use that catch of rainwater in some of the systems on site. We're also taking a preliminary look at solar energy. So we're looking at sizing, specific products, how we're going to use them. These are preliminary numbers, but we will take a further look at them in the near future. As for mechanical space, we want to focus on heat pump systems due to their high efficiency and their ability to use electric power. So we're looking at heat pump water heaters, air source heat pump, and we're also looking at an energy recovery ventilation system. Hopefully our deal with this is that we can actually get all these systems combined into one unitized system within a single room. So we can actually construct the whole system off-site, then move on to the site when it needs to be constructed and save on the cost there. And as per performance of our building, we found we had a HERS score of about 42 for an individual unit. And for the site, we found an EOI of about 27.73 kilobTUs per square foot per year. Now we want to get those numbers down in the near future. So we're aiming for a HERS score of at least 35 and an EOI of about 25 before we implement solar. We're also looking to improve our solar daylighting. We're only at about 20%, but we want to get closer to the 50% goal that we have. And in the future, we're hoping to improve our efficiency through things such as solar shading. We want to reduce our additional energy load, and we want to improve daylight for the space, as well as further figure out our mechanical systems. Thank you for allowing us to present. We hope to continue this in the near future.
Great, thanks team. And with that, we'll open up to our 2 panelists for questions.
Yeah, thank you. Great job. Question 1, were there any thoughts or did we evaluate, are we getting enough natural daylighting in the interior of the home where we're only getting, I don't know how the windows are only on one or the other side of the elevation, but the interior of the home, what are your thoughts on that?
Yeah, for the daylighting, so part of that is just that since we're in row housing, we're using those very thin, long units. It will be very hard to get that daylight in there. However, we are looking towards the lighter materials using inside the house to help reflect that lighting inside. And we're also going to try to use a clear story window to help open that up to the second floor too. And we're also possibly thinking about actually expanding a little gap by the stairs so we can actually get some of that additional sunlight to shine down into that first floor.
Okay, and appreciate it. My second question about the water, the rain catchment system. Were there any thoughts as far as treating that runoff or any of that water, whether it's being used in the home or in the surrounding areas?
We have considered a system in which we would filter that water and use it as gray water systems for, say, like toilets or laundry. However, we have to review some of the Indiana codes to make sure that it is compliant with codes.
Okay, thank you. Steve?
All right, thanks. I know in the presentation you said that there was a lack of affordable housing in Muncie. Is this going to be considered affordable?
Yes, we were planning on putting this as affordable housing. We did look into the comprehensive plan for Muncie, Indiana, and there is a lot of push. They have created a few overlay districts near the river. One of them is actually adjacent to our site. So this project is affordable housing, and it is something that's in alignment with the comprehensive plan for Muncie, Indiana as well.
Okay. I don't know. That was my biggest question on there. What were you, now that Alex opened the door to this, if you can't use your water that you're collecting as gray water, what are you going to do with it?
We have considered maybe using it for irrigation onto the site, but also we have also looked at a few rainwater strategies where instead of maybe collecting it and using it as catchment, we could just filter the water and try to control it on site to prevent flooding in the area. We are near the river, however, we are not in a 100 or 500 year floodplain. So we shouldn't have to worry too much about flooding, but it still is good practice to manage that stormwater on the site.
Okay. And are you guys confident that you can finish everything up by the deadline?
I feel pretty confident. I've been organizing our team so far with scheduling what project roles that we need done and then smaller areas. And so we do break them out into smaller tasks. And so we have a little chart and schedule going that we should be able to finish this with plenty of time at the end.
Okay, cool. I am good. Nice job.
Are you good too, Alex? Any more questions left?
Yes, I'm good. Thank you. Great job.
Thank you so much to Ball State. We'll take a few minutes here to just let the jurors wrap up any notes they might have. If Ferris State University would like to go ahead and start screen sharing, we will plan on getting started at 2:50 Eastern Time. All right, well, I'd like to welcome Ferris State University to the stage. And, please feel free to share your screen or to have your camera on, and we look forward to hearing your presentation.
Ready. Thank you for having us. Representing Ferris State University, we are the Euchre Troopers, and we bring you The Nest. Now, what is The Nest? It's our concept which involves renovating an apartment building with the goal of creating a net zero community sharing an independent grid of solar power. Another major goal that The Nest aims to achieve is providing that home away from home, which college students definitely need.
For the Euchre Troopers, I am Justin Cook as student lead, and then we have Becker Shakir in charge of design, along with David Besaw in charge of documents and analysis. We had a team advisor was our Professor Cosper. He was advising us throughout the course of this project. The overview is we are retrofitting a West Campus housing unit owned by Ferris State University in Big Rapids, Michigan. There are 22 buildings. This is the one that we were assigned to retrofit. The goal is to create a net zero building and to also improve the occupants' experience and engagement. Passive heating and cooling systems will be used along with an efficient HVAC system and an array of solar panels that will reduce the energy consumption of the building. There will also be an entertainment center added to the center of the building to encourage the community and occupants to engage in activities together and build a community within the units.
Our design goals going into this, we want to encourage community interaction. We want to produce a net zero building because we're in solar decathlon after all, and that is better for the environment in the future. And we want to improve the living spaces of the occupants that live there, while also lowering the cost for both the college student, the target market, and also the owners. This is one of many of the heat flux sensors that we've been using to help further develop this design goal and make it a reality. This will help us measure the actual R value of the current existing building. Our target market being the college student, they're typically aged from late teens to late 20s with some outliers. We can expect friends and family to visit. And due to us being college students, we don't have any money. And because of that, we want to make sure that the building's cost is lower for the college student. Our climate considerations. Living in Michigan, we have cold winters. We have actually surprisingly warm summers, high winds, and 31 inches of precipitation. In response to this, our design priorities are to keep the heat in, the cold out, and protect from cold winter winds, and to let as much winter sun in as possible. On the left, we have a graph showing our solar energy, and using this, we can see how much potential we can get from using solar panels on our building throughout the year in Big Rapids. On the right, we have precipitation, and using this graph, we will be able to see how can we react to this and address this issue of a large precipitation.
When it came to building code constraints, we wanted to keep the changes to a minimum when retrofitting the building. So we weren't too constrained with some of the changes we were making. One of the changes, the building we are renovating is ADA compliant. And when we wanted to retrofit it, we wanted to keep that compliancy. So those are codes we had to pay attention to, along with the parking lot being its maximum size per the area. So if we wanted to make any changes, we couldn't really alter the parking lot in any way. So we had to kind of leave that alone. And then for the maximum height of the structure, a local Big Rapids code had a height ceiling of 40 feet. So when redesigning the roof, we had to make sure that that was not exceeding the 40-foot limit.
As for our plans for the final submission, collectively, we intend to respond to any feedback from the occupants of the current building regarding their likes and dislikes of the building and its current state. We're planning on fine-tuning our cost analysis along the way, as well as completing a fully accurate 3D rendering of the building with accurate information regarding its insulation performance, as well as developing more ways to encourage interaction between occupants of the prospective renovation.
In terms of architecture, we're going to have three big things that you're going to be able to physically see, that being adding a back porch, we're updating the siding, and we're adding a shed roof. In terms of engineering, we have a system of a ground source heat pump with radiant flooring and a central air unit, and also reconfiguring the window placement to help get light into that building.
For our market analysis goals, we want to achieve a low maintenance cost to keep that monthly rent low for our occupants. We also want to use materials within the United States. Keeping local sources and everything like that is very important for us. For durability and resistance, we are trying to keep as much of the original structure there as possible. So using spray foam where we can to help without deteriorating too many of the exterior materials, along with adding a custom rain screen to the exterior to help buff out that precipitation that we get, and then updating the current insulation as much as we can within the building.
For embodied environmental impact, we plan on removing the use of natural gas, avoiding the use of any VOC paints, and utilizing local materials. For integrated performance, we plan on reducing the use of our HVAC system with the radiant floor, as well as installing a shed roof with solar panels at an optimized orientation.
For occupant experience, we intend to install a fresh, bright siding with the use of that custom rain screen. It will help bring light to the area. That back porch will help also in allowing the occupants to kind of interact with their local environment around them. And then we're going to install some outdoor grills even further than that to increase that immersion into their environment to help bond them as a community together.
For comfort and environmental quality, we plan on applying sound insulation either internally in the walls or externally. We plan on increasing natural lighting as well as adding a light color scheme throughout the interior of the building.
Our energy performance, our initial EUI score was 142. We want to achieve a score of 40 before we consider adding solar. And this was collected using Cove Tool as for the as-built model, and we plan on using it for the retrofitted building.
The West Campus apartment buildings are in close proximity to each other. There are 22. This means that if this building is successful, we can use it as a prototype to innovate the other remaining 21 buildings. We could use this neighborhood to set up a grid of clean energy buildings. And additionally, we improved the community awareness by creating one building at a time, but also installing a performance TV screen to where these occupants can kind of see how green their unit is versus the other units within the green buildings.
And in conclusion, we plan on creating a bright and open home away from home for incoming college students. And the success of this renovation can lead the way to a neighborhood of clean energy buildings successfully achieving the Nest's goal of being that home away from home.
Thanks so much, guys. Right on time. And with that, we will turn it over to our reviewers.
All righty. Thanks, guys. I appreciate the presentation. So the building itself, it's a townhouse, and each unit is 2 floors.
Yes.
Yes. Okay. So you said a couple things that I was a little confused about, I guess. First of all, it also looks like the building faces west for the most part, sort of. So, you know, you were talking about letting the winter sun in so that you can get the added heat there, which is great. Are we expecting people to occupy the building over the summer, though, when you really don't want that to happen, especially on that west elevation? And what were you planning on doing to maybe control that summer sun from overheating it?
So, sorry. So there was a monthly rent for the occupants of these buildings. So we're assuming moving forward that they are there year round, or at least the majority of them would be in and out year round. As far as the sun control, the porch will actually be on that west side of the building. It's kind of a back porch. And then the awning over that porch will hopefully kind of limit that amount of sunlight that's coming in the harsh summer days.
Okay. Okay. And then you also mentioned something about revising where the windows are located. You know, again, with it being a townhouse type setup and you only have windows on those 2 elevations, how much of that can you really do in moving the windows around?
For that one, we're hoping to enlarge the windows that are there, just make them as big as possible without, like, you know, violating the structural integrity of the wall. But the introduction of some hardwood flooring and lighter surfaces can also kind of increase that natural light reflection throughout the building. And then we were also looking into potentially adding some light shelf technology as well onto the edges of those window surfaces.
Okay. Go ahead, Alex. If we have some time, I can come up with another question or two, but I want to give you a chance.
Sure, Steve. Appreciate it. Great job, guys. It was mentioned about something on local materials. I guess in this design strategy, what are we considering leveraging that's locally available?
So for some of the materials with that, like we found some metal roofing company that was located in Michigan. And then when it comes to like the ground source heat pump companies and stuff like that, those ones are out of state. But we wanted to make sure that we could at least get like the bigger equipment from at least within the country. And then it was most of our like smaller materials like the wood flooring and stuff that we can implement that was mostly local within in-state.
Okay, thank you. And based on your remaining tasks, like the survey, are we on track as far as reaching a final completed design?
I would say so, yeah.
Okay. Thank you.
So if that's it for questions, I would like to say thank you so much to Ferris State University for your presentation. We'll give the jurors a few moments to just take notes. And then if Concordia University would like to go ahead and pull up their slides, we will be beginning that presentation at 3:05 Eastern time. Thank you.
Thanks so
again.
much.
Yes, thanks for having us.
Thank you.
Hey, Julia, can we ask a question from juror to juror?
Yes.
Okay.
Wait, who to us?
Can I ask Steve a question?
Yes.
Hey, Steve, on that last one, did you catch a floor plan?
No.
Okay. Thank you.
All right, I think we can start getting ready for Concordia University.
Ella, when you're ready. Okay. Okay, so hello, we're a team named Solar from Concordia University. We're presenting our attached housing design. So on the next slide, this is our team and for each section, and this is our interest partners. On the next slide, you will see our building is 12 units. It's located in Montreal, Quebec, Canada. Each unit is 3 stories high, plus a basement. It's located near Montreal Botanic Garden and Montreal Olympic Park, which would attract our main target market, which are young families. So for our building orientation, we have the weather data for wind, rain, sun, and photovoltaic potential. So for the wind, the building was positioned in such a way to minimize the effect of winds and wind-driven rain on the structure. As you can see on the slide at the bottom left, we have the year wind rose in Montreal, which shows the wind effects being higher in the southwest and west directions. And also on the side at the bottom on the right, we can see the sun. So to benefit from solar heat gain during long and cold winters, the building would have to face south. And to come up with a design solution, we analyzed the local geographic data and noticed that the average household size is of about 2 people per dwelling, and also that of those, there are 51% are children. Also, the average household income is of about $64,000
per family per year. But we also have to take into consideration that that region is under a great revitalization, and that 18% of the families earn over $100,000 per year. Another relevant data for our project is that married and common law couples make up 47% of the dwellings, and that 55% of the population in that area are between 20 and 49 years old. After identifying our target market, we went over the client's requirements, which are comfort, low initial and operational costs, and they also would like modern, urban, and spacious type of housing, but durable and efficient as well. And that led us to the climate requirements. We also discussed the construction industry challenges in Montreal, which are high housing demand, labor shortages, that high performance construction is still considered a premium, and that electricity costs in the future are unknown. So after taking all of these aspects and constraints into consideration, we came up with a question to answer. How do we get there?
To meet our requirements, we want an airtight, well-insulated building with reduced thermal bridges. This will cause us to have a lower energy demand and be able to size a smaller mechanical system. We will produce renewable energy on site, which will allow us to achieve a comfortable, efficient, and low-cost building. These steps will allow us to ensure durability, resilience, low carbon emissions, and be able to meet Canada net zero by 2050. For the structural system, we have a light wood frame structure for the 3 stories above grade, which is easily built and has a low cost. The foundation will include insulating concrete forms that will lower the labor costs and will be more energy efficient, as well as we will be using sustainable concrete that has lower CO2 emissions. All of our components will be sourced locally.
For the envelope system, we have opted for an exterior wall composition with straw bale, which is a byproduct that is easy to access. And this eco-friendly material releases less toxin and is also very customizable. Not only is it faster to construct with it, but it can also reduce material costs by acting as a structural element and insulation. And due to its compacted state, this material has a lot more fire resistance than a typical cellulose insulation. And with the continuity of our layers, we're expecting less thermal bridging. As for the roof, we have opted for a flat one, which is chosen for its simplicity to build, as well as less load being transferred to the structure compared to a sloped roof with extra stress to the foundation. It is also less costly, but still very high performing with a R value of 63. As for the windows, we have opted for triple pane, low E coating with argon gas with a U value of 0.736. And on the next slide, we have some of our main assembly compositions that are shown on the left. And on the right side shows the analysis of condensation through the Glaser method. And we have observed that there were no significant condensation throughout all these assemblies. As for the U values of our project, we have compared them to several baselines, such as the Canadian NECB code, Régie du bâtiment, ASHRAE 90.1, and we observed that we are in fact performing better in terms of thermal transmittance through all of these assemblies. Now moving on with the mechanical system.
In fact, as for the mechanical system, we opted to design a centralized heating and cooling source, which chose to install vertical closed loop geothermal system equipped with 12 boreholes, which are 242 meters deep. This centralized system will supply in cooling and heating the 12 units by installing one individual geothermal heat pump in each one of these units. Also, an integration of a BIPV system will also be conducted in the future to achieve a zero net energy building. As for the distribution system, we're going to use 2 pipeline coil units and diffusers. In fact, each one of the levels will be equipped of only 1 fan coil unit that will condition the supplied air, and then it will be distributed through different zones and spaces via the diffusers. This limitation of the number of fan coil units is really only done to reduce the initial high cost of this mechanical system. As for the ventilation system, a dedicated outdoor air system will be drawn to a ERV unit, which will be equipped to also a preheating coil that will temper the outside fresh air supplied. All of this equipment were sized and chosen to optimize not only the energy consumption, but to also comply with the constraints we faced in this building. And to do so, we did many simulations, such as a HAB simulation.
Based on our HAB design result, we got the load requirement and airflow rate for each room, each system, and each unit. As can be seen from the diagram, the load for each mid unit required 3.7 tons, and each corner unit required 4 tons. Based on those results, we determined the size of the equipment, including geothermal pump, fan coil unit, linear diffuser, and ERV with preheating coil. For HVAC energy simulation, the heating demand is 3.8 kBtu per hour per square feet, and each unit will spend $720 per year on their electricity cost. For the total initial cost for each unit, will spend $450,000, which include the structure system, envelope system, and mechanic systems.
To meet our requirements, we want to reduce the construction and labor demand, be cost efficient, and produce renewable energy to reduce carbon emissions.
And for our final steps, we will be adding the LCA analysis as well as finding partnership for the mechanical system and looking into the potential of implementing gray water system.
And by following energy efficiency standards and sustainability goals, we are actually committing to creating a more positive and lasting impact in our communities. Thank you.
Thanks so much, team. And we'll open up to questions from Alex and Steve.
Yeah, great job, everybody. Real quick on that thank you slide, what are all those numbers?
Colors.
The color code.
We
Color
use colors from an online source, so we are just referencing them.
Oh, okay, all right.
It's the reference.
Okay. So in the project summary, it was mentioned about heat waves and large volumes of rainfall in a single day. I guess, how does the design strategy address that, mitigate that, leverage that, those unique climatic events?
So by actually using some hangovers and balconies, we could reduce the direct rain into the building, into the envelope. That will help mitigate the moisture that goes through the envelope into the main insulation part, and also the position of the building. But basically, to be with external elements that will work as wind, rain, and solar prevention as well, shading.
Okay, thank you. That's all that I have. Steve?
Alrighty, thanks. Thanks, Alex. So obviously the envelope work that you guys did was excellent. I didn't see anything about the interior of the units at all. Is that designed?
Shirley, would you like to go over that?
For the interior?
Yes.
Yeah.
So we have some sort of partitions. We do have a partition wall, but we're still analyzing it because we're going to also look into like acoustics and other components.
Okay, not just the wall, but I mean like
the slab
and things like that,
if
floor
we have
plans,
any,
things like that.
we do have some sort of things done, but we just have to finalize it.
Okay, I didn't know if that was done and if you had taken the floor plan into account when you were estimating like operating costs and loads and things like that too. And I know somebody just mentioned shading, so that was another question that I had with the giant windows that you were showing on the front elevation that faces south. And you mentioned the flat roof. How much snow does Montreal get? And did that come into the calculation of whether or not a sloped roof might have been better just to try and avoid some of the snow load?
So we actually worked in partnership with our industry partner, who is an expert in envelope. And the flat roof is one of the most common solutions for Montreal in terms of costs and price. And it actually decreases the loads that go to the main structure. And so it's a kind of recommended for all the benefits and advantages when compared to the sloped roof.
Okay. Okay.
Yeah, so I can go to the, so this is what it looks like.
Yeah.
Yeah.
Okay.
Mhm.
All right. That was all that I had. Thanks.
Well, excellent. Are you, oh, Alex, we still have time if you'd like.
Oh, no. Yeah, thank you. Great job.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank
So
you.
thank you so much to Concordia University. I think we'll allow the jurors to take some notes, and then we're going to take a 10-minute break. So if people can plan on being back here by 3:30 p.m. Eastern time, we look forward to seeing you then.
Hey, all, we'll be jumping back in a couple minutes. If the team from App State is on the line, we can go ahead and pull up slides. We're gonna give them a couple minutes, but you guys look great and ready.
Can you guys see that okay?
Oh yeah.
Cool.
So yeah, we'll give everyone till 1:30, or sorry, 3:30 Eastern time.
Sounds good.
Thank you.
Oh no, Julia, I think it would have just been easier to do it your time and let us do the math.
Well, I just don't understand why they don't make PDFs yet where it just auto switches depending on what time zone you're on, right? Like we've got like AI that can like, make Shakespeare talk. You'd think we could just, have adaptable PDFs.
Yeah. I read something the other day. They said that, in Shakespeare's time, school was a lot easier, mostly because you didn't have to study Shakespeare.
That's funny.
I am a true engineer because I read Shakespeare and I take so long figuring out what the word is that I don't understand what it means after that.
It's been a long time since I read Shakespeare. Although sometimes, you read like words of chemical properties and you're like, this sounds like it could be like.
And I apologize for the cat jumping up on my desk. I'm used to it. It doesn't bother me, but I know here she is again. Not everybody is. So.
Oh, hello, cat. All right, we got 1 minute. Let's see, is Alex back? Alex, it appears to be back.
Yes.
Well, if you guys are ready, I think you could start.
All right. I am Elizabeth, the construction management team lead and part of co-operators from Appalachian State. Our project Parkway Commons is located in Boone, North Carolina. We are a multidisciplinary team of 24 students that are from 2 departments and 4 degree programs. We came together and began to work on January 17th and have made great strides in the last month.
Oh, sorry. Hi, I'm Emma, interior design. Here in Boone, we have a significant lack of affordable housing. Due to the lack of affordable housing, especially downtown, rent costs have skyrocketed to an all-time high. With the home prices being so high and only 6.8% of households having enough income to purchase their home, most people are choosing to rent. This has resulted in a 99.9% rental capacity and has around 35% of Watauga County's full-time workforce commuting into the county for work. At 24.5%, Watauga's poverty rate is almost double the national average. By working with the Watauga Community Housing Trust, we'll create an opportunity for increased affordable housing for families in need of a more affordable option. The Watauga Community Housing Trust is the nonprofit that works to provide low to moderate income families with stable, affordable housing. And after understanding our market and our client, we then tried to understand exactly who we would be designing for, which is based on the top employers in Watauga County, which are App State, Watauga City Schools, and Watauga Medical. This research eventually led us to pursue a co-housing model. Co-housing is a useful innovation for our design because it reduces the building's environmental impact, creates an affordable housing option, utilizes shared spaces, and fosters a sense of community. In order to reach these co-housing goals, we're working with modules that can be reconfigured depending on the building and user needs. We have a bedroom module, a living room module, and a wet MEP module that includes 2 back-to-back bathrooms and kitchens serving 2 separate units. In the co-housing space, we have an additional wet module that includes a larger shared kitchen, a bathroom, and a laundry space. The rest of the co-housing space includes living and dining areas on the first floor and additional living as well as private work areas on the second floor.
Hello, I'm Julia. I'm here representing the architectural team that's been working on Parkway Commons. So here you can see our site. Watauga County is in the process of potentially transferring this site over to the Community Housing Trust. The site is located just beyond Boone town limits, and it is a really cool site. It is right across the street from a significant park complex. There's multiple soccer fields. There's entrances to Boone's Parkway Trail, the headwaters of the New River. There's multiple bus stops and a local brewery right down the street. That being said, the site doesn't go without its challenges, in particular the very steep grade. We're also working with some resiliency issues relating to stormwater and risks and impacts of wildfires. In order for the site to work, we'll need to connect to the town's water and sewer lines. Conveniently, they are located right at the property boundary. This does mean that we need to adhere to the town's ordinances and restrictions. So our design concept is centered around and really draws inspiration from the Blue Ridge Parkway, which is a huge part of Boone. It is a historic scenic route that runs through the Blue Ridge Mountains in North Carolina and Virginia, attracts a large number of visitors. And our concept really embodies connection, flexibility, sustainability, and equitability. Just as the Parkway connects people to the many beauties of the Blue Ridge Mountains, Parkway Commons connects the community to many highlights of Boone. The Parkway provides flexibility and access to so many different places, and our project is designed to have that flexibility to be placed in a wide variety of sites and orientations. In considering sustainability, we are inspired by how the Parkway is woven into its environment and really works with its difficult surroundings. So our project, we are working with the site to promote healthy flows of water and energy. And just as the Parkway is accessible for everyone to use, Parkway Commons provides access to high quality housing for low to moderate income households. So our choice to explore volumetric modules is rooted in our commitment to reducing waste and really enhancing that element of sustainability. To achieve affordability and high quality in a challenging market, a flexible volumetric design can promote mass production for widespread application. Our current design incorporates a dwelling module, a fire-rated corridor, connected MEP module, and a communal space MEP module. And the remainder of that communal space takes a panelized approach.
Hi, my name is Aiden Hyder. I'm part of the engineering team for Parkway Commons. We are currently in the process of researching 2 different HVAC strategies. The first is a decentralized approach with packaged terminal heat pumps to serve the small heating and cooling loads of each dwelling unit. And the second one, in which we are very excited about, you can see on the slide here, is a centralized district energy system for the entire campus of buildings. This will entail having a large air-to-water or water-to-water heat pump that creates hot or chilled water that is sent to the dwellings via a variable primary flow pump system. Fan-cool units are installed in each dwelling unit to serve occupants' heating and cooling needs. Domestic hot water may also be produced through this system. We will leverage the central shared wall and the mechanical modules to distribute water, ventilation air from the heat recovery ventilator, and the stool and vent stacks connected to each unit. The central mechanical corridor innovation is the heart of this design strategy. The communal space will have its own systems in place, utilizing the aforementioned hydronic heat pump system. With this being said, efficient design of these systems will reduce operational energy.
When focusing on durability and resilience, we are paying close attention to control layers with our prefabricated systems. Moving forward, we are diving deep into the many connection points within our modules to ensure the building performs well into the future. In our foundation system, we have targeted a strip foundation with a stem wall, but when the grade is too steep, we are evaluating when to switch to a pier and beam. We have begun our hygrothermal analysis on the various building assemblies where we are looking at the durability under perfect construction conditions and if flaws are introduced. We want to prioritize the occupant experience by connecting residents to the outdoor environment. We are using biophilic design principles to incorporate areas of natural lighting, creating a community garden space, and optimizing views with glazing. Shared spaces bring the community together while showcasing our mountainous views. In these spaces, windows are positioned to facilitate natural cross ventilation. As required by the Zero Energy Ready guidelines, indoor air plus will be followed. With the assemblies of our modules, we have built-in acoustics with the installation used, and we are focusing on using Energy Star appliances to be more energy efficient. Capturing the uniqueness of our environment helps to create a home with an identity not like any other.
The presence of this larger communal space in our design has made residential energy modeling more complicated in terms of creating a specific HERS score for each dwelling unit. Preliminary steps have been taken to obtain individual HERS scores for each unit. In the next stage of our research, our team will obtain a HERS energy allocation for the communal space, which will then apply to each of our units. We will utilize eQuest to obtain total building energy to finalize our energy generation requirements. Simple tools like PV watts will be used to identify the total number of panels needed to achieve the target HERS score of 0.
Looking ahead, we plan to focus on finishing our master plan with our exterior designs and our mechanical systems. We want to meet with our client to critique and refine our schematic designs, and in finalizing our wall assemblies after conducting testing, we will create connection details and our exhibits. Here is a list of citations where we gathered statistics, and we are happy to answer any questions. Thank you.
Thanks, team. Perfect. And with that, we can hand it over to our two panelists for comments and questions.
And I lost track of who was going first this time, so I'll just jump in. Have you guys done anything with the rent? Do you know like how much rent this might end up costing? Just to kind of follow up with your affordable housing situation.
Yes, so we have met with some of the members on the Housing Trust, and as of right now, the targeted rent is going to be between $450 to $500 a month.
Okay, cool. That's really low. And then the whole co-housing situation there, I'm assuming, again, since you're working with the housing folks too, that that is a desirable living situation for people coming into your area.
Yes, it is. We want to focus, like using co-housing, we want to focus more on the efficiency of volume and space, and focusing on our community spaces rather than having, private spaces reduces the redundancy of like different spaces.
And while we were researching co-housing, we found that a lot of people that utilize co-housing spaces are either older individuals or like young couples or single people. So that's basically the main demographic in Boone and sort of the larger Watauga area. But with our site being in Boone, those two groups are the two main groups that live in Boone.
Okay, that's cool. Go ahead, Alex.
Yeah, appreciate it, Steve. Great job. Biophilic design. What specifically did the design bring into the project, right, for the building occupants?
So we want to focus on, connecting our residents to the outdoor environment as much as possible. So we are, we're going to currently be looking through different options where we can incorporate, our natural lighting, our natural ventilation, specifically with, with using the environment around the space. We want to do community gardens to connect each of the residents together. And we want to optimize the views, as we are in the Blue Ridge Mountains, so our views are very wonderful.
Thank you. Now, with natural ventilation was mentioned. In terms of wildfires, how does the design at that point address wildfires, especially indoor air quality?
So that is something that we are working on. We recognize it as a resiliency risk, and we are looking at different ways to target that, to reduce, to ensure that the air quality is as healthy as possible.
Okay, and lastly, the living building challenge was mentioned. Is the design strategy just focusing on one pedal or the entire certification?
Really the entire, or one pedal really. We're just looking into like having better indoor air quality and the system working better as a whole.
Okay, thank you.
We still have 50 seconds if anyone else has any questions.
One more from me. And I'm kind of assuming that your housing trust, I guess, is going to own the building. So I know you had talked about having a single like HVAC unit and everything for the entire building. Is it possible for them to do that and then just charge people like $50 a month as utilities, and then they pay everything else rather than have each individual tenant pay their own? That would help. I think that might help everybody with that. So I don't know if that was discussed when you were trying to figure out which way to go with your mechanical systems.
Yes, it was. That was an option that was talked about when we met. Was them, the residents paying for the utilities.
Okay.
Excellent. Thank you so much, Appalachian State University. Now we'll give the judges a few minutes to take down any notes they might have. And if University of British Columbia, Okanagan, and Thompson Rivers University, please correct me on my pronunciation. I'm sure it was wrong. If you want to go ahead and pull up your slides, and yeah, we'll get started at 3:45 p.m. Eastern time.
Thank you, guys.
Thank you very much.
Thank you.
Hi, thank you. The pronunciation was good for the name.
Okay. I didn't want to offend you by getting it wrong. I'm so sorry.
No worries.
All right. Well, let's give them another 30 seconds and then. All right, I think we could go ahead and get started.
Thank you. So Innovate, Design, Sustain is a team of students from diverse backgrounds representing the University of British Columbia, Okanagan, and Thompson Rivers University. We would like to begin by acknowledging that the land on which we gather today is the unceded ancestral traditional territory of the Silks Okanagan peoples. And we would also like to acknowledge that the proposed build site for river crossing is located on the unceded ancestral traditional land of Lytton First Nation, which is the ancestral territory of the Nkunklatma peoples. Lytton is a village in central British Columbia located at the confluence of the Fraser and Thompson rivers. This remote community is a heritage site and is one of North America's longest continuously inhabited areas. In June of 2021, a severe wildfire destroyed 90% of the village, forcing residents to leave their homes behind. Lytton has an arid climate and a temperature range of -4 to 120 degrees Fahrenheit. It is situated in a valley, resulting in high northward winds gusting up to 52 miles per hour. When we began the design of river crossing, we set out to answer three main questions. One, how can we rebuild the village of Lytton to be wildfire resilient and with a low embodied environmental impact? Two, how can we ensure our design is easy to implement and maintain in a remote location? And three, how can we design a high performance home to meet the community's unique needs?
To achieve these goals, we, 1, began the design with a non-combustible building envelope and implemented life cycle thinking early on. 2, we chose durable, market-ready building systems to reduce maintenance demand. And 3, we created an adaptable layout that can accommodate multi-generational family living or affordable rentals. Once this design is complete, it will be net zero ready according to the British Columbia STEP code. It will meet the standards of the US Department of Energy Net Zero Ready Home Program and be certifiable LEED Platinum. Families and seniors are the target market, and in 2026, 61% of home maintainers will be older than 65. River Crossing meets the needs outlined in the community plan by providing affordable family and accessible housing. In addition, our proposed rezoning from single-family residential to multifamily increases density near the city's core. River Crossing will be constructed for only $170 per square foot, further reduced by the Lytton Rebuild Program, which subsidizes non-combustible buildings.
River Crossing is inspired by the buildings that stood before it, ensuring community acceptance and connection. The design prioritizes functionality and allows form to follow. The elimination of complex junctions minimizes heat loss and unwanted noise. The 4 custom units have private outdoor spaces overlooking the Fraser River with interior design that promotes flow between rooms. The 3 family units include 2+ bedrooms, ample storage, a flex room, and an open concept living space.
The structural system of River Crossing eliminates structural concrete while using one of British Columbia's most abundant natural resources, timber. The structural materials are all manufactured within 125 miles of the site, supporting the local economy. Prefabricated open wall panels, roof trusses, and an I-joist floor system reduce waste. The steel helical pile foundation has an immediate load carrying capacity after installation, reducing construction time. The custom clerestory truss safely supports the photovoltaic array and snow loads according to the local code.
In the summer of 2021, there were over 300 wildfires in Canada. River Crossing demonstrates that it is possible to construct a uniformly non-combustible timber building in a high-risk location using market-ready materials. Non-combustible hardyboard cladding and a continuous layer of rock wool insulation reduce ignition risk and provide a 2-hour fire resistance rating. The Vulcan vents ensure that no stray embers penetrate the envelope, while exterior aluminum shutters protect the windows in extreme weather. Our remote-controlled leak defense system connects to the main water line to monitor appliances and pipes, preventing costly damage. Life cycle analysis is used as a tool in our iterative design process. Building materials like the 95% recycled aluminum standing seam roof promotes circularity. A preliminary life cycle analysis shows that the construction of River Crossing generates 51 pounds of carbon dioxide equivalent per square foot, 70% less than the standard Canadian 2-story low-rise. As the accuracy improves, we hope to reach below 40 pounds of carbon dioxide equivalents per square foot.
Air-to-air multi-zone heat pumps connected to remote-controlled thermostats give residents control of their interior climate. They can operate in temperatures colder than the historical minimum in Lytton, and backup heating ensures River Crossing adapts to changing environmental conditions. The heat recovery ventilators have air intake vents located at least 6 feet from the exhaust and filter up to 98% of particulates. Individual intake, return, and exhaust ductwork shown in blue, pink, and green respectively reduce the risk of fire spread between units. The air quality is further optimized by the heat pump's built-in dehumidification function and antimicrobial filters. The high-efficiency Sanco 2 hot water tank uses CO2 instead of refrigerant, while the drain water heat recovery system reduces energy consumption. Non-combustible acoustic insulation, floor underlayment, and electrical box putty pads create an effective sound barrier between units.
Accessibility is essential to social sustainability and multi-generational occupancies. Thus, river crossing includes a fully accessible unit, widened doorways, and entrance ramps. This unit has a 5-foot turn radius throughout, as shown by the green accessibility circles on the floor plan. Textured flooring adds visual interest while improving the grip of surfaces prone to moisture buildup. Variable height counters and electrical outlets create an inclusive space. Passive design helps meet river crossing's seasonal heating and cooling needs. The images on the screen show the solar intensity depending on the season. In the summer, the roof overhangs and balconies provide shading from direct sunlight to the lower floors and are bypassed by the winter sun to passively heat the space. The solar panels lay flush on the south roof, maximizing the size of the array and preventing snow buildup. The common vestibule prevents outdoor air from entering the units, reducing the HVAC load.
The solar array will produce 24,000 kilowatt hours per year and is connected to the grid using the local utilities net metering program. The buses and feeder cable sizes are based on the electrical demand calculated per the Canadian Electrical Code. Window placement at river crossing maximizes usage of available natural light. Task areas have concentrated lighting, while living areas have warmer light sources to provide an inviting atmosphere. River crossing is over 40% more efficient than the EnerGuide standard home. The envelope includes a continuous layer of exterior thermal insulation to mitigate thermal bridging. Hemp wool is selected as an interior thermal insulation as it has a lower embodied environmental impact than standard competing products while maintaining comparable performance. A preliminary analysis generated a HERS score of 29 before renewable energy generation, which will reduce as the accuracy of the model improves. Going forward, the performance of ENERGY STAR rated appliances will be compared. This iterative approach to energy modeling minimizes the energy use intensity of river crossing.
Our team works closely with industry and faculty advisors to ensure that river crossing is constructible and feasible to implement in the village of Lytton. As shown on the slide, we are currently finalizing our detailed engineering and generating final estimates. River crossing is a non-combustible timber building that can withstand the extreme climate. It is feasible to implement in Lytton using market-ready materials and can be scaled to other locations. River crossing proves that net zero ready, resilient homes do not have to be expensive or difficult to build and that they are market-ready in British Columbia. Thank you.
Thanks so much, team. With that, we'll open up to questions from our two panelists.
Yeah, great job. Quick question. Through this process and due to the events of what happened in 2021, is the building, is it sprinkled? Is there a fire sprinkler system?
No, so we have not decided at this time to include a fire sprinkler system in the building. Based on the British Columbia Building Code, it's not required for a residential building of this size. Our main focus has been making sure that the envelope is essentially impenetrable by fire. But in our next phase, that's something definitely we'll be looking into is how to improve the fire resilience of the interior of the home.
Right. And the other question or comment to that would be the focus of multi-generational accessibility, right? That begins to really look at the life safety component when we start to talk about fire sprinklers in addition to wildfires, right? Second question, let's see if I can pull it up here. Go ahead, Steve. I was making notes here. Let me pull it up.
That's all right. Thanks. Yeah, I know you have an air source heat pump that'll work down below the historical minimum of Lytton. Is there anything for supplemental heat for, all the extra cold weather we're getting in this climate change era?
Yes, so we will be providing electric resistive heaters as a low-cost backup heating option. Our heat pump is highly efficient. It has up to 75% efficiency in its coldest temperature range. So residents likely will not need it, but it is there in case. Okay.
And then I think it was in your project summary in the accessible units. And I didn't pull it up, but I think in the summary it said that the hinge door clearances were 2 feet. Shouldn't that be 3?
So if you go to Appendix 3, we designed accessibility based on the British Columbia accessibility codes.
Okay.
In our next phase, we're planning on looking more into the ADA. We've just recently started really, diving into that. So BC code is 2 feet clearances, the doors.
Okay. Okay. Yeah, sorry, I'm in the US. ADA is 3. I think it's either 3 or 32. Alex might know that, but those are the only questions I had. So go ahead, Alex, if you found what you were looking for.
Yeah, appreciate it. So going back to the wildfires, did the design look at anything in terms of mitigating the spread of fire beyond the building footprint itself? I don't know if there was a site plan or, but if the team could talk about that.
So Lytton has its own fire safety bylaws for the types and amount of vegetation that you can have, within the certain proximities of the building. So within 1.5 meters of the building, you can't have any vegetation. And then every species of vegetation is monitored by the village. So we have our own index of plants that we're allowed to use or not.
Okay. And lastly, going back to wildfires and the byproduct of wildfires, any thoughts on the indoor air quality during those events?
Yes, so our heat recovery ventilation system is fitted with MERV 13 filters, which filter up to 98% of particulates. And we believe that those, in addition to the silver ion filters in our heat pump, will provide sufficient indoor air quality for residents during fire season.
Okay, thank you. Steve?
I'm good. Excellent job, guys. Thanks.
Thank
you
you.
so
Thanks
much.
very much. Thank you.
Thank you.
Yes, thank you.
So special thanks to University of British Columbia, Okanagan, and Thompson Rivers University for their presentation. And in fact, thank you to all of the universities and colleges who came out and presented today. We were so honored to have you here. It was so impressive, the work you've done. And I look forward to continuing this tomorrow with you all. So we'll see you tomorrow, 10 a.m. Eastern time.
Thanks so much, teams, and really great work.
Thank you, Julia, Jeff.
Thank
Steve.
you, Julia, Jeff.
We'll see you guys tomorrow.
Alex. All right.
Thank you, Alex and Steve.
Have a good
Great
night.
questions.
Enjoy your evening.
Enjoy your evening.